Good day, everybody. Today we have a congruential equation or a modular arithmetic equation. And one thing to notice right off the bat here is that the 14 you see right here is actually 3 less than the modulus. Now that alone is not, you go, well, so what? But there is a result that's sort of like this, and it's famous result from number theory. If p is a prime, we have this result, which is in fact, it's necessary and sufficient conditions for a number to be prime. P minus 1 factorial is congruent to negative 1 mod p. Okay. Now this does say p minus 3, but this results. There's some manipulations we can do to make it reach this form here. It turns out. Now it's not immediately obvious, but again, this is called Wilson's theorem, and our approach will be to start with Wilson's theorem. Okay, again, this statement up here is Wilson's theorem. You'll notice right here that 17. This is 17 minus 1, right? 17 minus 1. Now. And I'll write this just for clarity. This is 17 minus 1 factorial. I'll just write 17 minus 1. But also notice that 17 is congruent to 0. Trivially, okay? 17 is congruent to 0. Mod 17, of course. And so you see how you can replace, in other words, since 17 is just 0, this would read 17 minus 1, right? But there's a 0 there. So you actually could replace 16 factorial with negative. You could replace 17 with negative 1. Now remember, folks, really this is just using the definition of the factorial function along with the fact that 17 is congruent to 0. Okay. Okay. Again, think of a 17 minus 1 being there. That is 16, right? But in the modular arithmetic world, 17 is congruent to 0. Okay. Okay. And a similar sort of process carries on all the way down. You could something similar happened doing this statement. Okay. Well, in fact, all we did was divide through by negative 1, which is okay in modular arithmetic, because think of it like this: if something divides a negative number, it also divides the number itself. That's more or less the reason why you can do that. Okay. Now. We get to this point right here. We have 15 factorial is congruent to 1 mod 17, and we do the very same sort of thing at this stage right here, because this would be 17 minus 2. Again, I'll quit yammering about the details, but this minus 2 you see right here is exactly this minus 2 right here. So we actually get to this statement right here. Now this next statement's a little tricky. We're trying to get 14 factorial isolated modularly so we can just substitute it back in. So, but why did I multiply by this crazy constant 9 right here? Okay. In other words, right here I multiply by 9. Well, notice that 9 times 2 equals to 18. But that's congruent to 1. Isn't that cool? It's called the multiplicative inverse. Okay? So that's what's so special about 9, right? That's what's so special about 9 right here. Now, so that's how this piece right here happened. You multiplied the 9 against the 1 also, you see. This negative 1 over here got multiplied by 9. That's what happened here. But 9 is congruent to 8. Now, we could work with negative 9. Most people prefer working with smaller positive numbers. And so we get this triumphant little result right here. Okay, so we know what 14 factorial is modulo 17, which is amazing, isn't it? 14 factorial is probably a number in the billions range somewhere, I guess, I think. Maybe not, but it's pushing, I think, because 10 factorial is in the millions, I believe. But anyway, so what we're going to do is just do a substitution into our original. Here's our original equation right up here. Original equation. Now we're raising 14 factorial to the 4th power, to the 3rd power, to see what it is. This is just the original equation. Now a very, very useful fact right here, let me write it somewhere we were okay right here. We replaced it with 8, right? Okay, that's because 14 factorial is 8. So we did this. Okay, and again, this is all congruent mod 17. I'm not writing it down for this to avoid clutter. Okay, now a nice result here that's going to help us out tremendously is that, let me write it right here, 8 squared, okay, 8 squared is equal to 64, right? But notice that that's congruent to 13. And you guys can verify that, okay? How do we know that? Well, that's the remainder you get when you divide 17 into 64. Another way of looking at it is 64 minus 13 is 51, which is a multiple of 17, okay? So we know that 8 squared is congruent to 13. So what do we get right here, folks? Let me just write right here. So we will have 13 squared right here, folks. You see the 8 to the 4th? Okay, 8 to the 4th is the same thing as 8 squared squared. So this will become 13 squared. And I'll just write this down one step at a time. We'll do it. Now, what do we have right here? 13 squared, or 8 squared is 13, and then times 8 again would be plus 104. And again, folks, to avoid clutter, I'm not showing every last bit of arithmetic, but hopefully you see where all this is coming from. This term right here is 8 to the 4th because 8 squared is 13. So you square 13 right here. You see, I didn't do the calculation just so you'd see. Now, 8 squared times 8 is 13 times 8, which is 104, right? And then right here, 8 squared is just 13. And then 8 is just 8, right? Minus 5, okay? So that's our work so far, okay? That's our work so far. And we're hoping this will come out to be 0 mod 17, okay? Now let's take a look here. Now this is 169. And again, I'll just write down 10 times 17, okay, is 170. 169 is 1 short of 170. So a little trick here is just to write 1 short of the modulus, which is 16. Okay, so I'm going to put 16 right here. Now you guys can check that a different way if you want to, but again, 13 squared is 169, right? That's just 1 shy of a multiple of 17, namely 170. So you can decrease the modulus. That's a nice little trick that helps you, and you can do a little proof on it if you want to. Now, what about 104? Okay, what happens when you divide 17 into 104? What do we get? Isn't 6 times 17 102, right? 6 times 17 is 102, so you would have a remainder of 2 right here, right? And then, okay, we still have the 13 going on right here. 13 minus 5. Okay, now all of this is just, let's see here. That's congruent to 18 plus 13 is 31. Okay, let's see. This is 16 plus 2 is 18. 18 plus 13 is 31. And then you get 5 right here. It looks like I may have, did I forget something here? Oh, I forgot the 8, folks. I forgot this 8, didn't I? Let's see here. 8 cubed. 8, no, I didn't. 8 squared. Oh, okay, I did forget this 8 right here. Okay, so let me put the plus 8, sorry. I'm not writing it in the right order, folks, but I think I just forgot to write this 8 down a while ago, right? It's because it's already reduced, right? Okay, so let's see what we end up with here. 18. This is 18. This is 31. 31 minus this is, so y'all, we get 34. Okay, 34. But guess what? That's a multiple of 17. Okay, so this is congruent to 0. And that completes what we're trying to do, okay? Because we wanted to show that 14 factorial is a solution to this, so we wanted it to reduce to 0 once we did all this work over here. And that's exactly what happened right here, folks. You could check my work, but couldn't be an accident, I don't think. 34 is equal to 2 times 17, so it's congruent to 0. And I'll just write here, go ahead and write mod 17. Okay, so that does it. And y'all, one thing I love about all this stuff is that think how big 14 factorial is. And nowhere in here do we get bogged down with huge numbers. The biggest computation we had was reducing 69 or 169 mod 17, which is that's very straightforward. Nothing was hard here. The magnitude of this number is unfathomable, but modular arithmetic allows us to go through and keep everything scaled down to very manageable arithmetic computations. So anyway, we did check that off, and that completes this problem. Okay, thank you for viewing.